Hello everyone. On today's lecture series, we are going to discuss about elementary idea of optimal load scheduling of hydropower plant. So, in the design thinking empathy stage, so what is the problem of the elementary idea of optimal load scheduling, especially for a hydroelectric power plant? So, here in the operator side, so what is free? But it will be limited. The water is free, but it is a limited one, and use it now or save it for peak hours by using the pumped storage hydroelectric power plant. And the consumers need, the demand varies every hour, but the supply must match the load as per the demand, or the grid which is fails. And according to the planners, the rainfall is uncertain. A reservoir level will change seasonally. So in the defense stage, what are we really solving? So here the total operating cost is minimized, the load demand is met at every hour, reservoir constraints are never violated, and water discharge is usually optimal. So in the ideate stage, we have to use some of the core concepts in order to go with the optimal load scheduling of hydroelectric power plant. So the water as an energy, the water, the potential energy of stored water, which will be converted into electrical energy via the turbines. And the scheduling horizon. A short term, it may be used hour-wise or daily, or it may be weekly or long term with respect to the seasonable planning windows. And the load curve. So hourly demand profile that a hydropower plant must track or supplement. And the reservoir model. The continuity equation governs inflow, outflow, and the storage volume, etc. So in the ideate stage, the optimization, the problem, the main objective function, which is to minimize the total thermal generation cost if we are implementing the hydroelectric power plant, because the hydroelectric power plant, the total cost is almost zero, because the water is a free resource. It may be in seasonably, or it may be sometime. Okay. So the fuel cost is equal to summation T is equal to 1 to T, CS of is equal to PS of T. So the C of S is nothing but thermal cost, and PS of T is nothing but thermal power at some time. So here the reservoir continuity. So V of t plus 1 is equal to V of t plus I of t minus Q of t minus S of t. So V is nothing but the volume of water, I is nothing but the inflow water to the reservoir, and Q is nothing but the discharge of water from the dam reservoir, and S is nothing but spillage. So here we have to maintain some of the key constraint. The power balance has to be maintained. That is nothing but the discharge. Actually, the P of H of T plus P of S of T. That is nothing but the discharge plus spillage is equal to the total demand. And the reservoir limit has to be maintained within the minimum and the maximum level. And the discharge limit also, generated limit also has to be maintained within a permissible level. Okay, so in the hydroelectric power generation, the power output of hydroelectric power plant, here the generator equation pH is equal to neta. Neta is nothing but an efficiency, and HQ. Here H is nothing but net heat, and Q is nothing but a discharge. And the simplified form, pH is equal to KHQ. So the K is nothing but neta, and the neta PG. Okay. So how do we solve it? So first of all, we have to classical methods. That we can implement the Lagrange multiplier or gradient search, or some of the analytical or closed form for simple terms. And we can use the dynamic programming method, that is breaks multi-stage problem into sub-problems. It handles non-linearity well. Or it may be we can use the meta-heuristic or heuristic, there is something but genetic algorithm or particle swarm optimization. It handles the complex problem real time world constraint effectively and efficiently. So in order to go with solving the Lagrange multiplier, so the first step we have to set up the Lagrangian, the attach the multiplier, that is nothing but lambda for power balance, for water usage constraint, and the second step differentiate with respect to discharge. And the third step, apply water availability constraint. The total water used over horizon T must equal available water. And the fourth step, ideate to find optimal schedule. So we have to go with the optimal schedule for optimal power generation at the minimum cost or no cost. The output the schedule. So hourly or weekly or it may be seasonably, we can implement this one with the minimize the cost and satisfies all constraints. So here an sample 3 hour scheduling example, our T is equal to 1, T is equal to 2, T is equal to 3. So one is off peak and T is equal to 2, it is peak hours and 3 is evening hours. So the maximum demand is given, hydro power plant demand is given, thermal power plant is given, and water meter per cube, the volume is also given. So here one hydro power plant plus one thermal power plant which is used to compensate the total demand. So the fixed heat assumption for 3 hour margin. So here we have to validate the schedule as hour by hour, or we have to verify the water budget, and we have to confirm the cost reduction, and we have to check the power balance equations also. So this can be used in the real-time applications like Bakranagal, India. The India's largest hydro complex daily scheduling balances irrigation as well as it can be used for the power generation. And Theri Dam, which will be located in the Uttarakhand, it will be a pumped storage hydroelectric power plant. Optimal scheduling decides when to pump and when to generate the electricity. And the three goals, which is located in the China, world largest hydroelectric power plant, that is sophisticated scheduling across seasonable flood cycles. So this is a mind map. So why we have to minimize the cost and why we have to meet out the demand and what is the concern and what is called quarter and what is objective, what is continuity and what is the governing relations. How we have to implement the Lagrangian dynamic programming iterative gamma method and what is the outcome? It may be an hour wise, week wise, or what is the cost saving, what is the labor operations, etc. And this is curated challenge. What if rainfall is uncertain? So at that time, what and how you will plan for the optimal load scheduling of hydroelectric power plant? This is another conceptual question. In the optimal hydrothermal scheduling problem using the Lagrangian multiplier, what is the physical interpretation of the water multiplier? If you know the answer, just to put in the comment section. And these are the few references for this topic. Thank you.